Okay, to really think about DeMorgan's Law, it's one of the least intuitive Boolean algebra laws or axioms you can have. And there's a couple of different ways to think about it. And one of them is more the mathematical way of thinking about it, and the other one is the graphical way of thinking about it. And so if I were to look at, say, the mathematical way of looking at it, there's basically two operations that you're going to do. So first, let's look at, my graphics tablet is not wanting to, okay, so we got A, B, and a line over both of them. Now what this literally means is, it's not really shown, but it's implied that because there's only one line that crosses both of these, then that means it's the output of this operation A and B that gets inverted. And so if I were to draw that as a diagram, it looks like this. Or, of course this is A and B. A quicker way of doing this is just to use a NAND gate. Now, if I were to want to convert this to something else, and you'll see how you can build any circuit with just NAND gates or with just NOR gates. And I'm going to show you how to go all the way to that point. But first we need to look at this, and one way of looking at this is what I like to call, you break the line and change the sign. So what this means is, if you want to distribute this inverse to each A and B before the operation, before in this case the AND operation, what you're going to end up having to do is change the AND sign to an OR sign. And what that would look like is A naught or B naught. So what we've done is we've split the line and we've changed the sign, and that distributes this inverse to each of these inputs. And the way that this would look would be, you got your A, and then you got your B going into an OR gate. And again, to kind of simplify that, we can just do a OR gate but have bubbles on the inputs, just to kind of clean that up a bit. Now all four of these circuits are equivalent circuits. They do the exact same thing. And as I said, it's not really very intuitive why this should work. It doesn't really just click in your brain, oh yeah, this is why that happens. But we can actually look at that and see why. So we can make a truth table and have A and B as our inputs. And then we'll have AB naught as one of our outputs. And then we'll evaluate A naught or B naught. And if you're ever confused over whether these things are the same or different, this is the technique that you would use to kind of prove it. Not just to yourself, but if you needed to prove it just in general, this is how you can do it. So we look at this operation. So A and B. And then we're going to inverse whatever A and B is to get the output of the NOR gate, or the NAND gate. So we say if A is a 0 and B is a 0, that should give us a 0 if they're just ANDed, but because of this line we have to invert it. And so that gives us a 1. Then if we have A is a 0, B is a 1, well, in an AND gate that would still give us an output of 0. So we invert that 0 to a 1 because of the line on top. Again, if we got a 1 for A but a 0 for B, that would give us a 0, but the 0 gets inverted, so that gives us a 1. And then finally, if A is a 1 and B is a 1, ANDed together, that will give me a 1. But because we got this inverter out here, then that will give me a 0. Alright, so that is in fact a NAND gate. So let's prove that this is the same thing as this inverted NOR gate, or inverted OR gate rather. So if we have A is a 0, B is a 0, if I say A naught, so that's a 1, B naught, that's a 1, 1 or 1 is going to give me a 1. And then if I have A is a 0, so that gives me a 1. And honestly, it doesn't really matter what B is, because anything or 1 is a 1. So I've got a 1. Again, same kind of thing. If A is a 1 here, that's a 0 over there, but B is a 1, invert that 1 to a 0 here, and you end up with a 1 there. So it's a 0, 1, 1, 0. And so this last one, if A is a 1, that becomes a 0. If B is a 1, that becomes a 0. So 0 or 0 is going to give me a 0. So these are in fact all the same exact circuit. So this means that there's actually a way that we can kind of manipulate this. Oh, this is just one version of the expression. Let me scroll down and show you the other way of doing it. So this is if you start with a NAND operation where the 1, and again, it doesn't have to be shown this particular way, it could just be shown this way, but the line is over multiple things. So if I come over here and show the other version of this, so this is A or B with a line over both of them. And again, what this is implying that you're taking actually the output of A or B and then inverting it. If I were to draw this, you have a regular OR gate with an inverter, or we can condense that to a NOR gate. Now again, this method that I'm mostly trying to show here is the mathematical version, and I'm going to go back and show you the simpler graphical way of doing this. So again, the thing to remember is this line is over both of these, so you need to distribute it, and in order to distribute it you have to break the line and change the sign. So I'm going to break that line and distribute it to both A and B, but I'm going to change this OR to an AND. So this means A naught and B naught. And notice how this is different than up here. We've got one line over the output basically, or one line over both of them, and we're breaking the line in half. So this up here does not equal the same thing as this. That's why this is not really that intuitive. So let's draw what this looks like. So this is an inverter and an inverter going into an AND gate. So we're inverting A and then inverting B, and then we're ANDing the results of those two things together. And then if I were to just kind of show this in a more of a shorthand method, do it this way. And so this is kind of the mathematical way, break the line, change the sign. Now I want to show you there's another way to do this. If I go up here to this NAND gate, and I want to mention again, all four of these are representations of a NAND gate. So if I have this NAND gate, or if I have this inverted OR gate, they're the same thing. And what I'm looking at is another way of looking at this is called the bubble method, or the push bubble method. And if I want to change this gate from a NAND gate into a inverted OR gate, or vice versa, what I'm going to do is I'm going to push this bubble through the gate this direction. And when you push the bubble through to come on the inputs, what's going to happen is it's going to change the type of gate that is. It's going to change it from an AND to an OR. And that works the other way around as well. I can just take these bubbles, if I wanted to shove them through to the output, I can do that, But whenever I do that, it's going to change to an AND gate as your base gate. And then the bubble comes out on the end over here. So there's the bubble method, and sometimes when you're given just a circuit, that's the easiest method to use. You say, oh, I've got a bunch of OR gates, or I've got a NAND gate, I need to change these. So you shove the bubble through, you change the type of gate that it is, and that's how you do it. And then this works as well over here with the NOR gate. I shove that bubble through so it comes out on the inputs, and then I have to change that to an AND gate instead. Now, forgive my doodling here, but that is supposed to be an AND gate. So that's another method. And again, if you wanted to super prove this, you could just simply build a truth table and just actually go through and, just like we did with the other gate, just actually evaluate it. So in this case, if I were to look at what a NOR gate does, so this is 0 and 0, so if A is a 0 or B is a 0, normally that gives you a 0, and you're going to invert that output, and so that's going to give you a 1. And then if A is a 0 and B is a 1, so if A is a 0, B is a 1, that's going to give you a 1 if you were just to OR those together. You invert that because of the line, and you're going to get a 0. And this is going to be the same thing because you're just switching which one of these is a 1 and which one is a 0, but it gives you the same result in this case. Finally, if you say A is a 1 and B is a 1, so 1 or 1 is 1, and that's inverted, so that's going to equal a 0. So that is in fact a NOR gates truth table. Let's look at the inverted AND gate over here. So the inverted AND gate, if A is a 0 and B is a 0, A becomes a 1, B becomes a 1, 1 and 1 is a 1. Now, if I look at this, any of these that become a 1 on your input get inverted to a 0, and anything and 0 is 0. So for the rest of these, we've got a 0 for A, so that becomes a 1, but B is a 1 to begin with. It turns into a 0 right here, and then anything and a 0 is 0. So we'll 0 that one. And the next one, again, is the same thing, but just different inputs. So you've got A is a 1, that becomes a 0. Anything and a 0 is a 0. And then here again, 1, 1 becomes 0, 0, and that's an output of 0. So these are all for the same circuit. Now, how can you build anything out of just all NAND gates and all NOR gates? Well, if I wanted to, let's just look at NAND gates. And this logic works the same way basically for a NOR gate. But if I look at an AND gate with an inverse on the output, something that's interesting about this is, I'm going to change color here real quick. If I go back up to this truth table, I can actually build an inverter with this pretty easily. And the way I can build an inverter with it is to get rid of these two center rows in the truth table. And the way to do that is just attach A and B together in the circuit. That way I only end up with either 0, 0, which gives me an output of 1, or 1, 1, which will give an output of a 0. And that's the exact same thing that you get with a inverter, right? So this is the truth table of an inverter. So if you look right here, if I'm only looking at instances where A and B are the same because I wired them together, so I get a 0, 0, that's going to give me a output of a 1. Or I have 1, 1 on the inputs, and that's going to give me an output of a 0. So that's going to give me the function of a inverter. So let me fix this because I need to wire these two inputs together. So if you just connect both inputs, that gives you an inverter. And then if we kind of look at, well, that's fine, I got an inverter and I've got a NAND gate. If I'm only using NAND gates, how can I build an AND gate? Well, an AND gate is a NAND gate with an inverter on the end, right? So that's actually going to give me, if I replace the inverter here with the NAND gate version of an inverter, that's going to give me a regular AND gate. Right? So now I've got, I'm going to kind of separate this a little bit. Oh, wait, I messed up. There we go. That's a regular AND gate here. So now I can say, oh, well, I've got a regular AND gate. I've got inverters. Well, I can build other stuff with that, right? If I look back up at these schematics that I've got here, I could say, what else could I build with AND gates and inverters? Well, I could build one of these, and that's a NOR gate. So let me take, I'm just going to copy that exactly as it is. And actually I'm going to tweak this a little bit, because so that's an AND gate. Well, I know that an AND gate is really a NAND gate with an inverter on the output, right? So if I were to use all NAND gates for this, I'm going to make NAND gate inverters on the input. And that's going to be the input of another NAND gate. That's the main NAND gate here. And the output of that, that should be the NAND version. And so this complicated looking thing is actually this circuit, which is actually this circuit, if you really look at it, which is actually a NOR gate. And just to complicate things a bit more, let's just make a regular OR gate, and then we have everything we need. So, oh, I need to do this is equal to a NOR gate. And I'm going to separate these a little bit. Oh, my graphics tablet's turned a little bit. Okay, so now I can come over here and I can say, well, I've got a inverter and a NOR gate, so now I can build a regular OR gate. Well, that's kind of goofy, because if I were to put an inverter on the end of this thing, then I would have two inverters here, and two wrongs make a right in digital logic. Okay? So these two inverters are going to cancel each other out, because if you invert an inverse, you're going to end up with the same thing you started with. So if I had a 0 coming into this, output's a 1, that 1 goes to the input of this one, the output's a 0. So really, it doesn't do anything. So I can just get rid of it. In fact, I can get rid of that entire inverter altogether, because I'm going to get rid of, I'm not going to add another one over here, right? That would just be redundant. So I'm going to remove all of those inverters on the outputs. So if I wanted to, I could just say, okay, well, this is a circuit like this, which, again, if you just build a truth table of it, will show you that this is, in fact, an OR gate. And to build it out of all NAND you do NAND inverters on the input, and then you would use a NAND gate for the main gate, and you're done. And that is your 2-input OR gate. So, by looking at this, really, if you're given a NAND gate, and again, this works for a NOR gate as well. If I just give you a NOR gate, you can turn it into an inverter. You can use that inverter with a NOR gate up here to build all these other gates. So, really, and NAND is the most common one that we use for this kind of thing. So that's really the one that most people focus on in class. But you're going to take this NAND gate here, turn it into an inverter, combine it with other NAND gates, and you're going to end up building all your basic gates. And all your basic gates can be used to build all logical circuits. And so, I mean, even if you wanted to do like multiple input gates, and I've run out of space here, I think. Let me scoot over. So if I wanted to do a 3-input NAND gate, or 3-input AND gate, rather. Well, to do 3 inputs, the way we typically will do a 3-input is, if we're just going to build it out of NAND gates simply, not really trying to optimize or anything like that, is if I'm only given 2-input AND gates, I'm just going to stagger them like this. So now that's a 3-input AND gate. Same thing for OR gates. So, you know, now it doesn't necessarily work like XORs or NORs or NANDs and that kind of thing. You kind of break that back down into their basic components, and then you'll put an inverter on the output of all that. But like for instance, if I want to turn this into a 3-input NAND gate, I just put an inverter on the output here. But that's how we can build 3-input gates, 4-input gates, 64-input gates, however many you want. In reality, that's not how we build them, like on silicon, but this is a good way to think about it, and the concept works because it's just a Boolean algebra association property, basically. So this is A and B, and then the output of that is ANDed with C. And then we're going to put a line over all of that. So that's what this gate is, which is just a 3-input NAND. And again, you could just build all of this stuff with AND gates, or NAND gates, rather. So I hope this kind of clears up a little bit of that information. The things that you're probably going to want to focus on are really the concept in general. If you just get the concept, you can design these and build them at will, but just like we did here. But if you're just going to try to memorize it, then these are the ones you should memorize, and then of course what they equate to. That's probably the easiest way to go about doing it. And of course, I don't have a NAND gate in this whole list because we started out with a NAND gate, right? We're just given the NAND gate to build all this other stuff out of. So, I mean, it exists, it's there, but you don't have to worry about it. And of course, XOR gates are, you can build XOR and XNOR gates out of just using regular logic to build it. So this is an XOR gate, and if I were to build this, to get this output, this is A naught and B, and then to get this output, I'm going to OR that with A, B naught. So that's your XOR, and then if you wanted to make an XNOR, that's just a truth table of 1, 0, 0, 1, and that is A naught, B naught, or A, B. There you go. Or you could just put an inverter on the output of that. Whatever you'd like to do. But yeah, so that's all the gates. You can basically build any of this stuff out of straight NAND gates. So, hope that helps.